Let's look at solutions of the matrix equation AX equals B. Recall that for an m by n matrix A, whose columns are A1 through AN, and a vector B in Rm, the matrix equation AX equals B has the same solution as the vector equation x1a1 plus x2a2 through xn equals b. The reason for that was the definition of the matrix product. A times x was by definition equal to the linear combination of the columns of A with weights given by the components of x. In fact, the following statements are equivalent, meaning the statements are either all true or all false at the same time. The matrix equation AX equals B has a solution. In other words, B is a linear combination of the columns of A, or in other words, B is in the span of the columns of A. How do you recognize whether for a given matrix A, the equation AX equals B has a solution for any choice of right-hand side B, not just for one given choice of right-hand side B? So let's look at an example. Here's a system of equations defined by a matrix times a vector equals to a right-hand side B. Recall that the corresponding vector equation is x1 times the vector 1, 0, 2 plus x2 times the vector 1, 1, negative 1 plus x3 times the vector -1, -3, 7 equals the vector 3, 0, 6. Let's solve this system by first writing down its augmented matrix, so the matrix A together with its right-hand side B. In order to bring this system into row echelon form, we want to create a 0 right here in that first column underneath that leading 1. To do so, we take the third row and subtract from it 2 times the first row, and we arrive at this system. Fortunately, we already have a leading 1 right here, so we'd like to create a 0 underneath it in this location. To do so, we take the third row and add to it 3 times the second row. The system is now in row echelon form, and we can find some solutions. The third row consists of all zeros, so it contains no information. The second row says that x2 minus 3x3 must equal to 0, and the first row implies that x1 plus x2 minus x3 equals 3. This means that we actually can choose x3 freely. This system does not determine what x3 is supposed to be. So we can choose x3 to be a parameter t of our choosing. And this parameter then determines x2 to be 3 times x3, which is 3t, as well as x1 equals 3 minus x2 plus x3, so 3 minus 3t plus t, or simplified 3 minus 2t. We see that we have infinitely many solutions because we can choose our parameter t freely. Next, let's look at a slightly different system. The system has the same matrix A that we began with earlier, but what's different now is the right-hand side B. I'm not going to go through the process of row reduction again. I'll just show you the end result. The end result is a matrix in which the last row has its first non-zero element in the rightmost column. This is an indication for the system having no solutions because the last row really reads that 0 must equal to -6, and we all know that that's impossible. So we started with a system that was very similar to the first system, just the right-hand side differed from each other, and on the second one we have no solutions. So what happened? We looked at a system AX equals B for the same matrix A, but for 2 different right-hand sides B. And we noticed several things. For the first right-hand side, the system has infinitely many solutions, whereas for the second right-hand side, the system has no solutions. The second right-hand side is therefore not a linear combination of the columns of A. And therefore, the columns of A do not span all of R3 because at least that second right-hand side is missed, which is a vector in R3 and not in the span of the columns of A. More generally, the following theorem is true. For a given m by n matrix A, the following statements are equivalent, meaning they're either all true at the same time or all false at the same time. If one statement is true, the other two must be true. If one statement is false, the other two must be false as well. Here are the statements. For each right-hand side b, the equation ax equals b has a solution. So that was not the case in the example that we just looked at, because we had one b for which the system had a solution and another one for which it didn't have a solution. So here the statement is that for each right-hand side, the system has a solution. That statement is equivalent to saying that each right-hand side is a linear combination of the columns of A. Again, that was not the case in the previous example. And this statement is equivalent to saying that the columns of A span all of Rm. Again, that was not the case in the previous example.